It started with a star, not a special star really, just one of 150,000 that the Kepler Space Telescope was watching. Its name was KIC 8,462,852, a little bigger than our sun, a little hotter. It was about 1,470 light years away in the constellation Cygnus. For years, it did what stars do. It sat there, then, in 2015, everything changed. A team of astronomers led by Tabetha Boyajian at Yale published a paper. The paper was about the light from KIC 8,462,852. Stars sometimes dim a little. It usually means a planet is passing in front of it. That's how Kepler found thousands of exoplanets. A planet like Jupiter might block about 1% of a star's light. It's a regular, predictable dip. A tiny shadow. But the light from this star was doing something else. The dimming was not small. It was huge. In 2011, its light dipped by 15%. In 2013, it dropped by a staggering 22%. A planet the size of Jupiter only blocks 1%. To block 22%, something would have to be 1,000 times bigger than Jupiter. That's not a planet. The dimming wasn't regular either. It was chaotic. It happened at random times and lasted for random durations from a few days to a week. Nothing in our models of planetary systems could explain it. The team checked for instrument errors. They checked for data glitches. They found nothing. The star was really behaving this way. Jason Wright, an astronomer from Penn State, saw the data. He and his colleagues had been searching for signs of advanced civilizations. They had a theory. An alien civilization would need vast amounts of energy. The biggest energy source in any solar system is its star. To capture that energy, they might build enormous structures around their star. These structures would block the starlight, or they would block it in a strange, irregular way as they moved and orbited. The data from KIC 8,462,852, soon nicknamed Tabby's star, looked exactly like what you'd expect from a swarm of alien-built megastructures. It was a wild idea, but no natural explanation seemed to fit. A swarm of comets. A giant dust cloud, a planet that got torn apart. Each of these ideas had major problems. The alien megastructure hypothesis, as unlikely as it was, remained on the table. It was the one explanation that couldn't be immediately ruled out. The search for extraterrestrial intelligence, or SETI, had suddenly shifted. We were no longer just listening for radio signals. We were now looking for shadows. The shadows of giants. Number 16... the Dyson Swarm is the most likely candidate. A single square meter solar panel in Earth's orbit receives about 1,361 watts of power from the sun. Our entire species, all 8 billion of us, used about 25,000 terawatt hours of energy in 2019. The sun puts out 3.8 x 10 raised to the power of 26 watts. In 1 second, the sun produces more energy than humanity has used in its entire history. A civilization that wants to grow will eventually need that energy. The physicist Freeman Dyson proposed a solution in a 1960 paper. He suggested an advanced civilization would eventually enclose its star with a cloud of orbiting habitats and power collectors. This is a Dyson Swarm. It is not a solid shell. A solid sphere is a common sci-fi trope, but it is a structural and gravitational nightmare. A swarm is different. It is a massive, independent collection of objects. Think of it like a dense, artificial asteroid belt. Each object could be a power plant, a habitat, or a factory. They would all orbit the star in different paths, at different speeds and different inclinations. This makes the system stable and scalable. You can start with one collector and add more over centuries or millennia. The signature of a Dyson Swarm is exactly what we saw at Tabby's star. The light from the star would not be blocked uniformly. As this cloud of objects orbits, different parts would pass in front of the star from our point of view. Sometimes a few small objects might pass, causing a small dip in light. Other times, a huge number of them might line up, causing a massive, irregular dip. The light curve would be chaotic, aperiodic, and deeply strange. It would look unnatural because it is. Detecting a Dyson swarm involves more than just looking at starlight dips, though. Any object that absorbs starlight must radiate that energy away as heat. Otherwise, it would melt, and physics demands it. This waste heat would be radiated in the infrared spectrum, so a star with a Dyson swarm around it would look dimmer than it should in visible light, but it would glow unnaturally bright in infrared. This is the key signature. When astronomers first looked at Tabby's star with infrared telescopes, they didn't find the expected strong infrared glow. This was a major point against the megastructure hypothesis, but it's not a deal breaker. A swarm could be designed to be cool, radiating at very long wavelengths that are harder to detect. Or perhaps it's not a full swarm yet, but a work in progress, so the infrared signal is still weak. The amount of material needed for a full swarm is immense. To build a swarm that would block a significant fraction of a star's light would require dismantling entire planets. The asteroid belt in our solar system, if ground up and used for solar collectors, would only block a tiny fraction of 1% of the sun's light. A civilization building a Dyson swarm would have to be a master of stellar system engineering. They would likely disassemble their gas giants or rocky planets for raw materials. This process of deconstruction might also be detectable. It could kick up enormous dust clouds, which could also contribute to the dimming of the star. It's a messy, colossal construction project that would be hard to hide. The idea was first inspired by Olaf Stapledon's 1937 novel Star Maker. Freeman Dyson simply applied the physics to it. He never imagined we would find a candidate so soon. And Tabby's star has since been explained by most astronomers as likely being a cloud of dust, but the dust model has its own problems, particularly with explaining the long-term, steady dimming of the star over the last century. The alien megastructure idea, while an extraordinary claim, forced the scientific community to take the search for large-scale astroengineering seriously. The Dyson Swarm remains the most plausible type of megastructure we could find because it's the most practical to build, and its signature is something we know how to look for strange shadows and excess heat. Number 15, the solid Dyson Sphere is a gravitational nightmare. A solid shell built completely around a star would have a surface area about 550 million times that of Earth, assuming it was built at our orbital distance. The tensile strength required to hold such a sphere together against its own gravity and the star's radiation pressure would be far beyond any known material. Even a hypothetical material made of pure nuclear strong force would be torn apart. But that's not even its biggest problem. The main issue with a solid Dyson sphere is gravity. From inside a hollow sphere, the gravitational pull from the shell itself cancels out. You would be weightless relative to the sphere. The star at the center, however, would pull on you. More importantly, the star and the sphere do not form a stable system. They don't orbit each other. The sphere is not gravitationally bound to the star in a stable way. If any part of the sphere gets slightly closer to the star, say from a small meteorite impact or a solar flare pushing on it, the star's gravity will pull stronger on that closer part. This would start a drift, the sphere would begin to move towards the star, and the process would accelerate. Without constant, massive course corrections, the entire sphere would inevitably collide with its star. This requires a system of active support. The civilization would need to have unimaginably powerful thrusters all over the surface of the sphere, constantly firing to keep it perfectly centered. The energy and complexity required for this station keeping would be colossal, perhaps even rivaling the energy output of the star itself. It makes the entire project seem inefficient and absurdly dangerous. So how would we detect such an object? It would be a very strange thing to find. A solid Dyson sphere would block all visible light from its star. From a distance, the star would simply vanish from the optical sky. However, the sphere would still have to radiate all the star's energy away as waste heat. It would be a perfect black body radiator, so we would detect a large, dark object in space that is glowing incredibly brightly in the far infrared with a temperature of a few hundred Kelvin, similar to a planet. It would be a star-sized object with a planet-like temperature. The IRAS Sky Survey in the 1980s was the first major search for such objects. It found none. Subsequent surveys have also come up empty. This absence of evidence is a strong argument that full, solid Dyson spheres are either extremely rare or non-existent. There are variations that try to solve the instability problem. One is a Dyson bubble, where the collectors are incredibly thin solar sails. The pressure of the starlight itself pushes them outward, balancing the star's gravity. This would require materials of impossibly low density, something like an exotic metal foil only atoms thick. Another idea is the Dyson net, a web of cables and collectors that would have huge gaps, making it less massive, but still prone to instability. The solid sphere is a powerful image, a symbol of ultimate technological achievement, but in practice it is a monument to inefficiency and danger. A swarm provides the same energy benefits without the catastrophic failure modes. If we ever find a sign of astroengineering, it's far more likely to be a messy, disorganized cloud of individual collectors than a perfect, monolithic shell. The universe tends to favor solutions that are robust and scalable, not ones that require constant, perfect control to avoid instant annihilation. The absence of these perfect infrared spheres in our sky tells a story. It suggests that either no one is out there, or they are smart enough not to build their house on a gravitational knife's edge. Number 14, a Shkadov thruster moves an entire solar system. A star can be turned into an engine. The concept, developed by Russian physicist Dr. Leonid Shkadov, does not involve consuming the star for fuel. Instead, it uses the star's own light. The device is essentially a gigantic mirror, a statite or static satellite. This mirror would be parked in a stable position over one of the star's poles. It would be huge, spanning a significant fraction of the star's diameter, but it would also have to be incredibly thin and light, like a solar sail. The principle is simple. The star radiates light in all directions. The mirror catches the light heading in its direction and reflects it back at the star. This reflection creates radiation pressure. Photons have momentum. When they are reflected, they transfer double their momentum to the mirror. This creates a net thrust. The mirror pushes on the star, and the star pushes on the mirror. Because they are gravitationally bound, the entire system, star, mirror, and planets begins to accelerate slowly in the direction opposite the mirror. The acceleration is tiny. For a sun-like star, the thrust would be on the order of 10 raised to the power of 18 newtons. While that sounds like a lot, a star is incredibly massive. The resulting acceleration would be about 10 raised to the power of 9 ms squared. It would take about 1 million years to change the star's velocity by 20 km/s. It would take tens of millions of years to travel 1 light year. This is not a system for fast interstellar travel. It is a system for galactic migration. A civilization might use a Shkadov thruster to move their home system out of a dangerous area, like a region with frequent supernovae, or to avoid a future collision with another star. Or perhaps they are simply moving to a more resource-rich part of the galaxy over cosmic timescales. How would we detect such a thing? It would have several distinct signatures. First, the star's light would appear asymmetrical. Half of the star's light would travel out into space normally. The other half would be blocked or reflected by the giant mirror. This would make the star appear to have a strange center of light that is offset from its center of mass. We could detect this through very precise astrometry, measuring the star's position and wobble. Second, the star would be moving in an unusual way. Stars in a galaxy generally orbit the galactic center in a somewhat orderly fashion. A star under the power of a Shkadov thruster would have an additional non-gravitational accelerations. It would be deviating from the expected galactic path. The Gaia Space Observatory is currently mapping the positions and velocities of over 1 billion stars with incredible precision. Its data is perfect for searching for stars with these strange accelerations. A few searches have already been conducted using Gaia data, but no conclusive candidates have been found yet. The mirror itself would also have a thermal signature. It would absorb some of the star's energy and re-radiate it as heat, likely in the infrared. Depending on its temperature, it might look like a large, warm object near the star that isn't a planet. The reflected light could also be detected. We might see starlight coming from a point where there should be none, or we might detect a slight red or blue shift in the light from one side of the star compared to the other. A Shkadov Thruster represents a level of engineering that is almost incomprehensible. The mirror would need to be built from materials harvested from the system's planets. It would have to withstand the intense radiation and solar wind from the star. It would need active systems to maintain its shape and position. But it is based on known physics. It requires no new science, just an immense scale of engineering. It's a subtle form of megastructure. It doesn't scream for attention like a Dyson Sphere. It just quietly pushes its home through the void, a silent ship on a voyage of 1 million years. Number 13, stellar engines are more than just mirrors. A Shkadov Thruster is just one type of stellar engine, a megastructure designed to move a star. There are other more complex designs that could be more efficient. These are often called Class A stellar engines, as defined by the physicist B.W. Enevoldson. A Shkadov Thruster is a Class B engine, relying only on radiation pressure. Class A engines use the star's own matter as fuel. One common concept is a Kaplan thruster, proposed by physicist Matthew Kaplan. This engine would use a massive structure to collect stellar wind, the stream of charged particles flowing out from the star. It would use a set of huge electromagnetic fields, like a magnetic scoop, to funnel this material, primarily hydrogen and helium. This collected matter would then be used to fuel fusion reactions in a massive fusion engine. The engine would generate 2 powerful jets of particles. One jet would be fired straight into the star to prevent the engine from falling into it. The other jet would be fired out into space, providing the main thrust to move the system. This design is much faster and more efficient than a Shkadov thruster. A Kaplan thruster could accelerate a sun-like star to much higher velocities, potentially reaching a few % of the speed of light over millions of years. This would allow a civilization to travel between galaxies over cosmic timescales. It's a tool for escaping a dying galaxy or colonizing a new one. The detection signatures would be dramatic. The engine itself would be a massive heat source glowing brightly in the infrared. More obviously, we would see the jets. We see astrophysical jets coming from black holes and young stars all the time. But a jet coming from a normal main sequence star with no accretion disk would be a dead giveaway for artificial activity. The jets would be highly collimated beams of particles, and they would likely emit radio waves and other forms of radiation that we could detect with radio telescopes. The star's chemical composition might also be altered over time, as the engine selectively funnels and fuses elements. Another type of stellar engine would use a Dyson Swarm not just for energy, but for propulsion. The swarm would collect energy and then use it to power a massive laser or particle beam, pushing the star forward. This is similar to a light sail, but instead of pushing a small craft, it's pushing the entire star. This would also have a clear signature, a star that is inexplicably bright in one specific direction, or a star whose light appears to be focused into a beam. These engines are not just about moving a star. They are also about controlling it. An advanced civilization might use these technologies to stabilize their star, extending its lifespan by billions of years. They could lift heavy elements from the star's core, preventing it from aging as quickly. They could manage its solar flares and coronal mass ejections, creating a perfectly stable environment for their home planets. The engine is a tool for control, turning a wild star into a domesticated power source. Looking for stellar engines means looking for stars that are not behaving as they should. We look for stars with strange velocities, unnatural jets, or asymmetrical light patterns. These are signs that something is manipulating the star, imposing its will upon the nuclear furnace. We haven't found any yet, but as our telescopes get more powerful, our ability to spot these subtle manipulations will grow. A star moving of its own accord would be one of the most profound discoveries in human history. It would mean someone is at the helm. Number 12. A Matryoshka brain computes on a planetary scale. The need for energy is one driver of a civilization's growth. The need for computation is another. A Matryoshka brain is a hypothetical megastructure that uses the entire energy output of a star for one-purpose computation. It is the ultimate supercomputer. The name comes from the Russian Matryoshka dolls, the nested dolls that fit inside one another. A Matryoshka brain is a series of nested Dyson Spheres or Swarms. Each layer is a shell of computational machinery. The innermost shell would be built close to the star. It would run incredibly hot, powered directly by the star's raw energy. The computer components on this layer would be designed to operate at thousands of degrees. This layer would perform its computations and then radiate its waste heat outwards. The second shell would be built further out. It would be designed to absorb the waste heat from the first shell. This heat would then power the computations on the second layer. This second layer would operate at a lower temperature than the first. It would then radiate its own, even cooler waste heat outwards. This continues with a third shell, a fourth, and so on. Each successive layer is larger and cooler than the one before it, absorbing the waste heat of the inner layer and using it for its own processing. The final, outermost layer would radiate heat at just a few degrees above absolute zero, making it almost perfectly efficient. The computational capacity of such a structure would be astronomical. It's hard to even put a number on it. It would be able to simulate entire universes, support the consciousness of trillions of digital minds, or solve problems that are far beyond our current understanding of physics. A civilization might choose to upload their consciousness into this machine, abandoning their biological bodies to live forever in a simulated reality of their own design. For such a civilization, the physical universe becomes just a power source for their internal one. Detecting a Matryoshka brain would be challenging. Like a Dyson sphere, it would block the star's visible light. The star would disappear, but its thermal signature would be unique. Instead of radiating at a single temperature like a simple Dyson sphere, it would radiate across a wide spectrum of infrared wavelengths. Each shell would radiate at a different temperature, creating a complex, layered thermal signature. The most telling sign would be the final waste heat from the outermost shell, which would be extremely cold, radiating in the far infrared or microwave part of the spectrum. It would look like a large object that is barely warmer than the background temperature of space itself. Finding one would require sensitive infrared and submillimeter telescopes. We would be looking for a dark spot in the sky that has a strange, multi-layered heat signature. It wouldn't look like a star, a planet, or a dust cloud. It would be its own category of object. The structure might also have subtle gravitational effects on nearby stars, but these would be hard to distinguish from a normal dark object like a brown dwarf or a cold gas cloud. The Matryoshka brain represents a possible endpoint for a technological civilization. A culture might decide that exploration of the external physical universe is less interesting than the exploration of the internal computational universe. Or they might retreat into their machine, a silent, thinking god orbiting a captured star. From the outside, their system would go dark and cold. They would seem to disappear. But inside, they would be more alive than ever. Our searches for extraterrestrial intelligence often assume that aliens will be trying to communicate. But if a civilization has built a Matryoshka brain, they may have no interest in talking to us at all. They would have their own richer universe to explore. Number 11, a birch planet is built around a black hole. Stars are not the only power source in the universe. For a truly ambitious civilization, even a star is not enough. The most powerful engines in the cosmos are supermassive black holes. A birch planet, a concept proposed by the author Paul Birch, is a megastructure built around one of these monsters. It is a shell world similar to a Dyson sphere, but it encloses a supermassive black hole instead of a star. The energy source is the black hole's accretion disk. As matter falls into a black hole, it forms a spinning disk of superheated gas and dust. The friction and gravitational forces in this disk can heat the material to millions of degrees, causing it to shine more brightly than an entire galaxy of stars. This is what powers quasars, the most luminous objects in the universe. A civilization could build a shell to capture this immense energy. A birch planet would be the largest conceivable artificial object. A supermassive black hole can be billions of times the mass of our sun. Or a shell built around it would have a surface area trillions of times that of Earth. It would be large enough to be a home for countless species, a manufactured galaxy in itself. The shell would need to be built outside the black hole's Roche limit, the point at which tidal forces would tear it apart. The engineering challenges are of course extreme, but the structure has some advantages over a stellar Dyson sphere. The central object, the black hole, is a point mass. This makes the gravitational environment much more stable. The shell could be made to rotate, creating artificial gravity on its inner surface. The rotation speed would need to be close to the speed of light to counteract the immense gravity of the black hole. This time dilation would mean that time on the birch planet would pass much more slowly than in the outside universe. 1,000 years for the builders might be 1,000,000 years for the rest of the galaxy. How would we detect such an object? A birch planet would fundamentally alter the appearance of a galactic center. Supermassive black holes are usually found at the center of large galaxies, including our own Milky Way. We observe them by watching the stars that orbit them and by detecting the radiation from their accretion disks. A birch planet would block all of this. The galactic center would go dark. The characteristic X-rays and radio waves from the accretion disk would vanish. The rapid, tight orbits of stars like S2, which orbits our own Sagittarius A, would be obscured. The shell itself would radiate waste heat, just like a Dyson sphere. Given the immense energy of a quasar, the birch planet would be an incredibly luminous infrared object. It would be one of the brightest things in the sky at infrared wavelengths, yet completely dark in the visible spectrum. It would look like a galaxy's core had been replaced by a giant warm sphere. The sheer scale of it would be hard to mistake for a natural object. The existence of a birch planet would imply a type the third civilization on the Kardashev scale, one that can harness the energy of an entire galaxy. Such a civilization would likely have colonized or engineered much of its host galaxy. The birch planet might serve as its capital, its central computer, or its final home. It is a structure of such scale that it borders on the mythological, but it is consistent with the laws of physics. If a civilization has the time, the resources, and the will, it is something that could be built. Searching for them means looking at the hearts of distant galaxies and asking, is anyone home? Number 10, an Alderson disk is a world without a horizon. Imagine a record, a giant vinyl record. Now imagine that the hole in the center is a star. The record itself, a vast flat plain of rock and soil, is the world. This is an Alderson disk, named after its inventor, Dan Alderson. It is a colossal artificial structure, a disk with a thickness of thousands of miles. The star sits in the middle, and the habitable zone is a ring on the surface of the disk. The scale is difficult to comprehend. The outer radius of the disk would be roughly equivalent to the orbit of Mars or Jupiter. The surface area would be many millions of times that of Earth. You could have entire continents, oceans, and civilizations on this disk and never run out of room. There would be no horizon. The ground would just stretch out flatly forever. Far in the distance, the ground would curve up slightly, eventually becoming a wall of sky. Life would exist in a temperate ring on the disk. Too close to the central star, and it would be a scorched desert. Too far out, and it would be an icy wasteland. The star would not rise and set. It would hang perpetually in the sky at the center of the world. To create a day-night cycle, the civilization might build a giant orbiting shade or cause the star itself to pulsate. The disk would be so massive that it would have significant gravity of its own. An object on the surface would be pulled down towards the disk's center plane. While building an Alderson disk would require more mass than is available in most solar systems, it would likely require the mass of several gas giants, or perhaps even a small star. The material strength needed to keep the disk from collapsing into the star or tearing itself apart would be immense. The outer edges would be moving faster than the inner edges, creating enormous shear forces. To counteract this, the disk would likely need to be made of exotic, ultra-strong materials and possibly be supported by a network of fusion reactors or other active systems embedded within it. Detecting an Alderson disk would be a strange exercise. From far away, if we were looking at it edge-on, it would look like a line cutting across a star. It would produce a very unusual transit signal, a long, flat dip in starlight that could last for weeks or months as the disk passes in front of its star. If we were looking at it from above, it would be harder to see. The star in the middle would be visible, but it would be surrounded by a huge, dark, cool disk. The disk would have a thermal signature. The side facing the star would be warm and would radiate in the infrared. The side facing away from the star would be cold. The spectrum of light we receive from the system would be a mix of the star's light and the infrared glow from the disk's surface. This composite spectrum would look very different from a normal star with a protoplanetary disk. A protoplanetary disk is made of gas and dust and has a specific chemical and thermal signature. As an Alderson disk would be a solid object with a much more uniform temperature profile in its habitable zone. The gravitational effects would also be a clue. The disk's immense mass would cause the central star to wobble in a very specific way. It would also perturb the orbits of any other objects in the system, like outer planets or comets. An Alderson disk is a statement. It's a civilization that has decided to pave over its solar system, turning it into one contiguous piece of real estate. It prioritizes living space over everything else. It is a world built for expansion, a flat Earth on a cosmic scale. Number 9, a ring world orbits at 1 million miles per second. A ring world is a classic megastructure popularized by Larry Niven's novel of the same name. It is an artificial ring about 1 million miles wide, built around a star at a distance of about 93 million miles, the same distance as Earth from the sun. The ring would be spinning. This spin would create artificial gravity on the inner surface through centrifugal force. To simulate Earth's gravity, the ring would need to be rotating at a speed of about 770 miles per second, or nearly 1.2 million kilometers per second. The inner surface of this ring would have a surface area of about 3 million Earths. It would be a ribbon of a world with 2 towering walls, 1,000 miles high, at each edge to hold in the atmosphere. The star would hang motionless at the center. To create a day-night cycle, a set of large orbiting shadow squares would circle the star closer in, casting a manufactured night across sections of the ring as they pass. The material science for a ring world is even more extreme than for a Dyson sphere. The tensile strength required to hold the ring together against the immense centrifugal forces would be godlike. Niven invented a fictional material called skrith for this purpose. No known material could come close. If the ring were to break at any point, the entire structure would fly apart catastrophically. Despite the material challenges, a ring world is more gravitationally stable than a solid Dyson sphere. However, it is still not perfectly stable. Like The sphere, it can drift. A small nudge could cause it to drift into its star. Niven addressed this in the sequels to his novel, introducing a system of massive thrusters on the ring's edge to maintain its position. These thrusters were disguised as mountains. Detecting a ring world would depend on its orientation. If we see it edge on, it would periodically block the star's light. But unlike a planet, it would block the light from both sides of the star as it orbits. We would see 2 dips in the light curve for every one orbit, and the dips would be flat and long, corresponding to the width of the ring. If the ring is tilted relative to our line of sight, it would present a constantly changing profile. It would block a variable amount of light as it rotates. More importantly, it would reflect starlight. A ring world would be an enormous, flat, spinning mirror. We would see flashes of reflected starlight, a phenomenon known as specular reflection. The light from the star system would appear to pulse or flare on a regular schedule corresponding to the ring's rotation period. Its thermal signature would also be distinctive. The ring would absorb sunlight and re-radiate it as heat. It would be a huge infrared source, but in a very specific shape. With a powerful enough telescope, we might be able to resolve it not as a point or a sphere, but as a thin, glowing line or ellipse in the sky. A ring world is a compromise between a planet and a Dyson sphere. It provides a massive amount of living space with Earth-like gravity, but it doesn't require enclosing the entire star. It's an elegant, if fragile, solution to the problem of a growing population. Finding one would be finding a piece of cosmic jewelry, a shining band built by artists as much as engineers. Number 8. A topopolis is a sprawling cosmic city. Imagine a pipe, a very long pipe. Now imagine this pipe is bent into a loop and placed in orbit around a star. The pipe itself is rotating, creating artificial gravity on its inner surface. This is a topopolis, also known as a cosmic spaghetti. It is a type of O'Neill cylinder, a spinning space habitat, but stretched out to an astronomical scale. A topopolis could be thousands of miles in diameter and millions, or even billions, of miles long. You know, it could be wrapped around the star multiple times like a ball of yarn. This would create an absolutely immense amount of living area, all with artificial gravity and a controlled environment. The interior could be landscaped with forests, oceans, and cities. Because it is a closed environment, the climate could be perfectly regulated. Unlike a ring world, which has open skies, a topopolis is an enclosed tube. The sky would be the other side of the tube, thousands of miles away. The civilization could simulate a sky on the inner surface, or they could simply have a view of the distant inner wall of their world. To get sunlight, the tube would need to have massive windows or a system of mirrors to pipe light in from the outside. A day-night cycle would be easy to create by simply rotating shutters on these windows. A topopolis avoids some of the stability and material strength problems of a ring world. And because it's a tube, it is structurally stronger, and because it can be routed in a more complex path, like a figure 8 or a torus knot, it can be made gravitationally stable without the need for constant station-keeping thrusters. As it is also modular, a civilization could start with a small section and just keep adding to it over time, extending the tube indefinitely. Detecting a topopolis would be tricky. It is a much thinner structure than a ring world or a Dyson sphere. If it's wrapped tightly around its star, it would look a lot like a Dyson Swarm. It would block the starlight in a complex, irregular way as it rotates and orbits. The light curve would be chaotic. The main difference would be in the thermal signature. A Dyson Swarm is a collection of many small, hot objects. A topopolis is one long, continuous object. Its infrared signature would be more uniform. With a powerful enough infrared telescope, we might be able to resolve its shape as a long, thin filament of warmth wrapped around the star. If the topopolis is in a wider orbit, it might be easier to spot. As it passes in front of the star, it would create a very sharp, deep, and relatively short dip in the starlight. By observing multiple transits, we could map out its shape. If it is wrapped multiple times, we would see multiple transit events for each orbit. The structure would also have gravitational effects. It would be a huge amount of mass in a very specific shape. It would affect the orbits of any planets in the system in a way that a spherical planet or a diffuse dust cloud would not. Precise measurements of planetary orbits in a distant system could reveal the presence of a massive thread-like object. A topopolis is less of a grand statement and more of a practical, sprawling metropolis. It's a structure for a civilization that is constantly growing and expanding. It's the ultimate urban sprawl, a city that has wrapped itself around a star. It's a sign of a civilization that has chosen to build up and out, creating a continuous world without end. Number 7, artificial black holes could be tiny power plants. All of the megastructures discussed so far are about harnessing the power of large natural objects like stars and quasars. But what if a civilization could create its own power source? What if they could build a miniature black hole? An artificial black hole would be the most efficient energy source possible. According to Stephen Hawking, black holes are not completely black. They radiate energy known as Hawking radiation. The smaller the black hole, the hotter it is and the more radiation it emits. A black hole with the mass of a large mountain would have a temperature of billions of degrees and would radiate immense amounts of energy in the form of gamma rays and other high-energy particles. It would be a tiny star-like power source. Creating such an object would require technology far beyond our own. We would need to compress a mountain's worth of mass into a space smaller than an atom. This would likely require incredibly powerful lasers or particle accelerators focused on a single point. Once created, the black hole would begin to evaporate through Hawking radiation. To keep it from disappearing, the civilization would have to constantly feed it matter. This process of feeding the black hole and harvesting its radiation would be their power source, and it would convert matter to energy with nearly 100% efficiency, far surpassing nuclear fusion. A civilization with this technology could place these micro black holes wherever they needed power. They could be used to power starships, cities, or even terraforming projects. They would be portable, controllable suns. Detecting these artificial black holes would be a search for specific types of radiation. A small evaporating black hole would end its life in a flash of gamma rays. The final burst would have a very specific energy signature. Our gamma-ray telescopes, like the Fermi Gamma Ray Space Telescope, are constantly scanning the sky for such events. So far, the gamma-ray bursts we have seen are all attributable to natural phenomena like supernovae and neutron star mergers. But a burst with the right signature, coming from a place where nothing else seems to be happening, could be a sign of an artificial black hole expiring. A black hole being used as a power plant would have a different signature. It would be a constant source of high-energy particles and gamma rays. It would look like a point source of immense energy, but with no visible star or galaxy associated with it. Well, we would be looking for isolated, high-energy objects. The problem is that many natural objects, like pulsars and microquasars, also produce high-energy radiation. We would need to analyze the spectrum of the radiation very carefully to see if it matches the theoretical profile of Hawking radiation. Another way to detect them would be through their gravitational effects. Even a small black hole has a powerful gravitational field. If an artificial black hole were part of a starship, it would cause the ship to have a strange gravitational signature. It might also be used as a weapon fired at a planet or a star. A small black hole passing through a star would cause a massive and very unusual flare-up of energy. The search for artificial black holes is a search for the pinnacle of energy technology. It is looking for a civilization that has mastered the fundamental properties of space-time itself. They would no longer be tied to their home star. They could take their power with them, creating oases of energy anywhere in the cold, dark void of space. Number 6, a Klemperer rosette is a dance of artificial worlds. A Klemperer rosette is not a single object, but a collection of objects in a remarkably stable and beautiful configuration. It consists of an even number of celestial bodies of 2 different masses, heavy and light, orbiting a central point in a repeating pattern. For example, you could have a heavy planet, then a light planet, then a heavy planet, and so on, arranged in a circle. If the masses and distances are just right, the system is stable. Each body's gravitational pull is perfectly balanced by all the others. This concept was first proposed by Wolfgang Klemperer in 1962. A natural Klemperer rosette is unlikely to form. The conditions for its stability are too precise, but an advanced civilization could build one. They could move planets or build artificial habitats and place them into this stable configuration. It would be an artificial solar system, a piece of celestial clockwork. It could be a way to create a system with many habitable worlds, all in close proximity to each other, allowing for easy travel and communication. The central point of the orbit might be empty, or it could contain a central star. If there is a star, all the planets in the rosette would share it, orbiting it as a single stable unit. Or the planets themselves could be the power source. Perhaps the heavy bodies are artificial black holes, providing energy to the light bodies, which would be the habitats. Detecting a Klemperer rosette would be a matter of finding a system with an impossibly regular arrangement of planets. Our own solar system is messy. The planets are at irregular distances, with varying masses and orbital inclinations. A Klemperer rosette would be the opposite. It would be a picture of order. We could find it using the transit method. As the rosette orbits its star, its planets would pass in front of it. We would see a series of perfectly regular repeating transit signals. If the rosette contained, say, 6 planets, we would see 6 transits, all equally spaced in time. The transit depths might alternate between deep for the heavy bodies and shallow for the light bodies. This kind of perfect regularity is not something we expect to see in a natural system. We could also detect it through radial velocity measurements. The gravitational pull of the planets in the rosette would cause the central star to wobble. The pattern of this wobble would be very complex, a superposition of all the individual orbits. But it would also be perfectly periodic. A Fourier analysis of the star's velocity would reveal a series of strong, sharp peaks at specific frequencies corresponding to the perfectly ordered orbits of the rosette members. If the rosette does not have a central star, it would be much harder to find. It would be a collection of dark objects moving through space together. We might find it through gravitational lensing. If the rosette passes in front of a distant star, its combined gravity would bend the starlight, causing a complex and unusual magnification event. Or we might only find it if it happens to pass through our own solar system. A Klemperer rosette would be a sign of a civilization that values order, stability, and community. It is a system built for cooperation, a federation of worlds bound together by a shared, elegant dance of gravity. It would be a quiet testament to a society that has learned to engineer not just objects, but entire systems. Number 5, Globus Cassis is an inside-out world. The Globus Cassis is a concept developed by the architect and artist Christian Waldvogel. It is a proposal for a future human megastructure, but an alien civilization could build one as well. It is a hollow, compressed, and buckled sphere. Its most radical feature is that it would be built using all the matter from its home planet. The planet would be deconstructed and reformed into this new world. The structure is a large, hollow icosahedron, a 20-sided shape with large openings on its faces. The interior surface would be the new living space. The sun's light would enter through the large holes. Gravity on the interior would be produced by the mass of the structure itself, but it would be much lower than on the original planet. The atmosphere, water, and biosphere would all be moved to the interior of this new world. The core of the old planet, its magma and iron heart, would be used to create small suns or light sources inside the structure to illuminate the areas that don't receive direct sunlight. The result is a world that is much larger in surface area than the original planet, but also one that is entirely artificial and self-contained. It is an act of ultimate recycling, turning a chaotic planet into an ordered habitat. Detecting such an object from another star system would be difficult. If a civilization converted its planet into a globus cassus, the planet would simply vanish. We would see a rocky planet in the habitable zone of a star, and then one day it would be gone. The process of deconstruction would likely create a massive dust cloud, which would temporarily obscure the star. We might see a star suddenly dim, and then when the dust clears, one of its planets is missing. This would be a shocking and unmistakable sign of astroengineering. The globus cassus itself would have a unique signature. It would be much less dense than a normal planet. If we could measure its mass through its gravitational pull on the star and its radius through its transit, we would find that its density is impossibly low. It would be a planet-sized object with the density of styrofoam. Its transit signature would also be weird. A solid planet creates a smooth, U-shaped dip in starlight. A globus cassus, with its massive holes, would have a much more complex transit profile. As it passes in front of the star, the light would first dim, then brighten slightly as a hole passes by, then dim again. The light curve would be full of notches and bumps. Its thermal signature would also be strange. The interior would be warm and habitable, but the exterior would be cold, facing the vacuum of space. The structure would radiate heat, but in a way that is very different from a planet with a uniform surface temperature. The heat would mostly come from the openings. It might look like a cold object with a few hot spots. The globus cassus is a philosophical statement as much as an engineering project. It represents a civilization turning inward, choosing to perfect its own world rather than expanding outwards. It's a kind of cosmic terrarium. Finding one would be like finding a ship in a bottle, a miniature, self-contained world, a sign of a civilization that decided to rebuild its home from the ground up. Number 4 terraforming markers are planetary scale construction sites. Before a civilization builds a megastructure around their star, they might start with their own planets. Terraforming, the process of engineering a planet to be more Earth-like, would require massive engineering projects that could be visible from interstellar distances. These projects would leave behind detectable artifacts, or terraforming markers. One of the most significant markers would be the use of orbital mirrors or shades. To warm up a cold planet like Mars, a civilization might place huge, thin mirrors in orbit. These mirrors would reflect additional sunlight onto the planet's surface, melting ice caps and thickening the atmosphere. These mirrors would be highly reflective. As they orbit the planet, they would flash. We would see regular bright flashes of reflected starlight coming from the planet. This would be very different from the steady faint light reflected by the planet itself. The flashes would be specular reflections, like the glint of sunlight off a distant window. A program called the Search for Extraterrestrial Visible Emissions, SEVE, is designed to look for exactly these kinds of flashes. Conversely, to cool down a hot planet like Venus, a civilization might build a sunshade. This would be a huge, dark object placed between the planet and its star, casting a shadow on the planet. This shade would be detectable. As it orbits, it would block light, not just from the planet, but also from the star. It would create its own tiny artificial eclipse. We would see a small, sharp dip in the starlight every time the shade passes in front of the star. It would look like a very small, very fast orbiting and unnaturally dark object. Another marker would be changes in a planet's atmosphere. Rapid, large-scale terraforming would involve pumping massive quantities of specific gases into the atmosphere. For example, releasing huge amounts of perfluorocarbons, PFCs, powerful greenhouse gases, to warm a planet. These are artificial chemicals that do not occur in nature. The James Webb Space Telescope is capable of analyzing the atmospheres of exoplanets. If it were to detect massive industrial-scale concentrations of artificial compounds like PFCs or other pollutants in a planet's atmosphere, it would be a very strong sign of industrial activity. We might also see direct evidence of construction. Massive engineering projects on the surface of a planet, like building canals, moving mountains, or constructing continent-sized cities, would change the planet's albedo, or how it reflects light. As the planet rotates, we would see its brightness and color change in a way that does not correspond to natural features like oceans, continents, or clouds. The light curve of the planet itself would be unnatural. These terraforming markers are signs of a civilization in its adolescence. It has mastered its own planet and is now beginning to engineer its solar system. It has not yet reached the stage of building Dyson Swarms, but it is on its way. This might be the most common stage for a technological civilization, and therefore the one we are most likely to detect. And we are looking for the cosmic equivalent of a construction site, the dust, the noise, and the glint of new tools under a distant sun. Number 3, interstellar beacons could be disguised as pulsars. Much of SETI has focused on listening for deliberate messages, radio signals sent with the intention of being heard. But a message can be more than just a radio wave. A truly advanced civilization might build a beacon that is so powerful it can be seen across the galaxy. They might do this by modifying a natural celestial object, turning a cosmic lighthouse into a signaling device. The perfect candidate for this is a pulsar. A pulsar is a rapidly spinning neutron star. It has an incredibly strong magnetic field that channels beams of radiation out from its magnetic poles. As the star spins, these beams sweep across space, like the beam of a lighthouse. If one of these beams happens to sweep across Earth, our radio telescopes see a regular pulse. Pulsars are the most precise clocks in the universe. Their pulse rates are incredibly stable. An advanced civilization could modify a pulsar to send a message. They could do this by placing a large object or a cloud of plasma in orbit around the pulsar. As this object passes in front of the pulsar's beam, it would block it, causing a missed pulse or a change in the pulse's shape. By controlling the orbit of this object, they could turn the pulses on and off, creating a pattern. It would be like interstellar Morse code. How would we know it's artificial? The signal would be encoded in the timing of the pulses. Natural pulsars are very regular, but they do have a tiny amount of timing noise. An artificial signal would be too perfect. It might contain a recognizable mathematical pattern like the sequence of prime numbers or a complex non-random string of on-off signals. We have been monitoring pulsars for decades. If one of them suddenly started missing pulses in a structured way, it would be a major discovery. Another way to modify a pulsar would be to directly interfere with its magnetosphere. A powerful enough energy beam or magnetic field could alter the way the pulsar emits radiation. This could change the shape, polarization, or frequency of the pulses. The civilization could modulate the pulsar's beam itself, encoding a message directly onto the signal. This would be a much more sophisticated method. We would detect this as a pulsar that is not behaving according to the known laws of plasma physics. Its signal would have an artificial complexity to it. Why use a pulsar? Because they are incredibly powerful and long-lasting. A pulsar's beam can be detected from thousands of light years away. They will continue to spin and emit for millions of years. It's a beacon that is built to last. It is also energy efficient. The civilization is not creating the signal from scratch. They are simply modulating a pre-existing, powerful natural signal. The search for these pulsar SETI signals is an ongoing effort. Astronomers look for anomalies in the timing data of the thousands of known pulsars. So far, all observed variations can be explained by natural causes, like the presence of orbiting planets or instabilities in the neutron star's interior. But the search continues. A pulsar that winks at us in binary code would be an unambiguous "we are here." Or it would be a message written in the language of collapsed stars. And number 2, star lifting would leave scars on a star. A civilization building megastructures needs materials, a lot of materials. Planets are a good source, but the ultimate source of matter in any solar system is the star itself. Star lifting is the process of deliberately removing matter from a star. A civilization might do this to acquire specific elements, like hydrogen for fuel or heavier elements for construction. They might also do it to manage their star's evolution, extending its lifespan or preventing it from becoming a red giant. There are several proposed methods for star lifting. One method, proposed by David Criswell, involves using powerful magnetic fields. And a ring of powerful electromagnets would be placed in orbit around the star's equator. These magnets would create a strong magnetic field that would interfere with the star's own magnetic field. This interference would cause the star to eject a stream of plasma along its rotational poles. This stream of hot gas could then be collected and processed. Another method would use powerful lasers or particle beams. A massive orbital station would fire a beam at a point on the star's surface. This would superheat that spot, causing a massive eruption of stellar material like an artificial solar flare. This material could then be scooped up by other collection vehicles. The signatures of star lifting would be dramatic and hard to miss. We would see a star that is behaving very strangely. If a civilization is using the magnetic method, the star would have a highly unusual magnetic field, one that is not symmetrical and does not match stellar models. We would also see massive continuous jets of plasma shooting out from the star's poles. These jets would be much larger and more persistent than natural solar flares. If they are using the laser method, we would see a star that has a single incredibly hot spot on its surface that is not a sunspot. This spot would be the target of the lifting beam. We would also see frequent, massive eruptions originating from that one spot. Over time, star lifting would change the chemical composition of the star. If the civilization is selectively removing certain elements, the star's spectrum would begin to look very strange. For example, if they are harvesting helium to use in fusion reactors, the star would become depleted in helium relative to other stars of its type. This is known as peculiar stellar abundance. Some stars with unusual chemical compositions have been found, like Przybylski's star, which contains strange, short-lived radioactive elements. While natural explanations exist, advanced stellar engineering is a fringe possibility. Star lifting is a sign of a civilization that is not just living in its solar system, but actively farming it. They are treating their star not as a god or a passive source of light, but as a mine, a raw material to be exploited. It is a sign of a very advanced, very industrial, and perhaps very desperate civilization. Finding a star with these kinds of scars would be like finding an open pit mine on a cosmic scale. It would tell us that someone is not just building, but consuming their world. Number 1. Nicole Dyson beams can sterilize planets across galaxies. Or take a Dyson Swarm. The swarm collects a significant fraction of a star's energy output. Now, instead of using that energy to power computers or habitats, focus it. Use a massive phased array laser or particle accelerator powered by the entire swarm to turn the star's energy into a single coherent steerable beam. This is a Nicole Dyson beam. It is the ultimate weapon, a Death Star that uses a real star for power. The power of such a beam would be almost unimaginable. It could be used for many purposes. As a propulsion system, it could launch a light sail starship to relativistic speeds, allowing for rapid interstellar travel. A single beam could power a fleet of ships across the galaxy. It could also be used for communication. A beam of this power could be seen from billions of light years away. It would be the ultimate beacon, a signal so bright it would outshine its own galaxy for a brief moment. But its most terrifying application is as a weapon. A Nicole Dyson beam focused on a planet could boil its oceans and strip its atmosphere in a matter of hours. It could be used to destroy enemy fleets, demolish planets, or even destabilize other stars. It is a tool for projecting power on a galactic scale. The existence of such a weapon has profound implications for the Fermi paradox, the question of why we don't see signs of alien life. Perhaps the galaxy is quiet because powerful old civilizations use these weapons to eliminate any potential competition. This is the Great Filter, as an act of cosmic warfare. Detecting a Nicol Dyson beam would be a shocking event. If the beam were to sweep across our line of sight, we would see a star suddenly and dramatically increase in brightness. It would not be a supernova, which has a specific light curve and spectrum. This would be a sudden, intense flash of coherent monochromatic light, like a laser. It would be a completely unnatural event. The star might appear to become one of the brightest objects in our sky for a few minutes or hours, and then fade back to normal. If we are not in the path of the beam, we might detect its use in another way. When the beam is activated, the Dyson Swarm that powers it has to reconfigure itself to focus the energy. This might cause the star to suddenly dim or blink out as the swarm's mirrors or collectors all turn to face the target. We would see a star that is there one moment and gone the next, only to reappear later. This is different from the chaotic dimming of a normal swarm. It would be a sudden, coordinated disappearance of the star's light. The search for such events is part of what observatories like the Vera C. Rubin Observatory will do. It will scan the entire sky every few nights, looking for transient events, things that flash or change. It is designed to find supernovae and asteroids, but it is also perfectly suited to find the signature of a Nicol Dyson beam. Finding such a beam would be the most profound and terrifying discovery in human history. It would prove that we are not alone, but it would also prove that the universe contains technologies of incomprehensible power and potentially incomprehensible malice. It would be a warning, a sign that the silence of the galaxy might be a silence that is enforced. The final megastructure on this list is not a home or a computer or an engine. It is a gun, and it is pointed out at the stars.